Hi, I'm Matthew. Today we're going to be talking about virtual memory and page tables. So first we need to go over what is virtual memory. So virtual memory is in a specific process. The process, when it is written, or whenever you're writing a program, you don't know what sort of system the process is going to be run on. And so when we have instructions such as loading and storing from a specific address in memory, you don't know whether there might be other processes running on the same computer that would also want to access that same spot in memory. And at the same time, there's a variable amount of RAM that could be installed on any computer. Some have 4 gigabytes, some have 8 gigabytes, 16 gigabytes. And so a specific process can't be written knowing what sort of memory addresses will be available to it on the actual computer when the process is being run. To get around this, processes and programs are written so that they use virtual addresses. And then the virtual addresses of a whole bunch of different programs can overlap as much as they want. And then what the computer does is when processes are actually running, it translates each process's virtual address to an actual physical address in physical memory that stores the values for each process. And the way these addresses are translated from virtual addresses to physical addresses is through the page table. Each process has its own page table, which it uses to translate its virtual addresses to the physical addresses associated with it. So how does it do this? Start off with, we can assume, say we have a 32-bit virtual address. When we're talking about page tables and storing memory, we always assume that memory is stored in pages. So if you have an address that is 32 bits wide, a virtual address, the last number of bits will be reserved for the page offset. And then whatever is left at the beginning is the virtual page number. Oftentimes, the size of a page will be given to you in a problem. A common page size is 4 kilobytes. And to index into 4 kilobytes of byte addressable memory, you would need 12 bits. Because that's 4 kilobytes is 2 to the power of 10 times, well, 2 to the power of 2 times 2 to the power of 10 bytes. So you need 12 bits to be able to index into a 4 kilobyte page size. And so in this specific example, our virtual address would have 12 bits at the end reserved for the page offset, and then the actual virtual page number would be 20 bits. And what we would do if we wanted to translate this virtual address that we have into a physical address is we would go to our page table and figure out what physical page number corresponds to this virtual page number, and then we would just take that physical page number we get, tack on the page offset, and go to that spot in physical memory. The way page tables, or at least the most basic page table works, the single level page table works, is that you'll just have an array in memory where within the array you store the physical page numbers associated with a whole bunch of virtual pages, and then you index into this array with your virtual page number. So you would go to whatever index is associated with the virtual page number, and you would get the physical page number that is stored there to translate it into a physical page, and then you would take that physical page number, append to the page offset, and that's where you would go in memory to get the data that you want. Now, of course, in situations like this, where we have 20 bits for our virtual page number, that would mean we need 2 to the 20th page table entries in order to actually accommodate all the virtual pages in this system. So that's not a very good system, because that means our virtual page table will be incredibly large for every single process. To reduce the size that we take up in the general case of a page table, we can have multi-level page tables, where we split up the virtual page number into segments and use each segment to index into a different virtual page table. So to sort of go over how this works, let's say this is the virtual page number, and we split it up into 2 parts. The first level and the second level. And in this case, let's just assume that both of those take 10 bits. Then we could have our first level page table that we index into with our first level bits. We would index into our first level page table like that. Inside the first level page table isn't the physical page number yet. It would be a pointer to where the second level page table is that we would index into with the second level offset. So we would go, let's say these bits were like 00011 with a whole bunch of zeros at the beginning. If this was our first level page table, we would go to offset 11, so 00. We would go here. This would have a pointer to some second level page table. And then we would index into this second level page table with the second level offset. And so if this was like 00001, we would go to this spot, and this is where the actual physical page numbers would be stored now. They wouldn't be stored in the first level anymore. First level stores pointers to the second level page tables, and then the second level page table stores the actual physical page number, and we would take that physical page number, and we would append on the page offset, and that would be the physical address that we go to for this virtual address. So in the worst case, you could end up with as many second level page tables as there are first level page table entries, but the key is that you only need to create and allocate second level page tables as you need them. So in the common case, when you're only accessing a few first level entries, this system is a lot more space efficient than if you had just one single level page table which needs to accommodate every single possible virtual page. So now that we've gone over the basics of how virtual memory works and page tables work, let's jump into an example problem that may come up on homework or exam. So now let's go over a common type of virtual memory problem. We have these specifications for the actual virtual memory system, and we want to answer all of these questions. So to start off with, we want to know how many virtual pages and how many physical pages there are in our system. To answer that question, we're going to need to know about the actual total size of virtual memory and physical memory and the page size. Because if we want to know the number of pages, we can take the total size of virtual memory and divide it by the page size, or take the total size of physical memory divided by the page size to find the number of virtual or physical pages. So virtual memory, we know we can index into virtual memory with 48 bits. That means that in total, we have 2 to the power of 48 virtual addresses. Or in other words, we have 2 to the 48 bytes in virtual memory. And then we know that our page size is 8 kilobytes. And 8 kilobytes is 2 to the third times 2 to the 10. And that's for one page. So when we divide this out, we can do 48 minus 13, gives us that there are 2 to the 35th total pages in virtual memory. And then we can do the exact same thing for the number of physical pages, except instead of dividing the virtual address size or the virtual memory size by the page, we can divide the physical page, or the physical memory size, which is 16 gigabytes, by the page size. And so 16 gigabytes is 2 to the 4th times 2 to the 30th. And then we can divide that again by our page size, which is 2 to the 13th. And so that's 34 minus 13 gives us 2 to the 21st pages in physical memory. So I'll just write these down here. We have 2 to the 35th virtual pages and 2 to the 21st physical pages. A lot fewer physical pages than we do have virtual pages. So now we want to figure out how many bits are used for the offset into a page. And to answer that question, we just need to worry about how big a specific page is. So the number of bits we need to index into a page, we look at the page size. Our page is 8 kilobytes large, which again we said before was 2 to the 3rd times 2 to the 10th is 2 to the 13th bytes per page. And then to figure out how many bits we need to index into that, we just take the log base 2 of that. So log base 2 of 2 to the 13th is obviously 13. And so we need 13 pages of every address to index into our page. So the number of bits used for a page offset is 13. And now let's look at the number of bits that we would use to index into our first level page table. To figure out how many bits we need to index into our first level page table, we need to figure out how many first level page table entries there are. So we know that our first level page table takes up exactly one page total. So the total size of first level is one page, which is 8 kilobytes, which is 2 to the third times 2 to the 10 bytes. And then we can divide that by the size of one page table entry, which we are given as 8 bytes. Or we could think of that as 2 to the third to make it easier. And that means that in our first level page table, we have 2 to the 10th entries total. And so if we have 2 to the 10th entries total in our first level page table, the number of first level bits, the number of bits from our address that we use to index into our first level page table needs to be enough to index into 2 to the 10th entries. So that's log base 2 of 2 to the 10th, which is, of course, 10. 10 bits of our virtual address will be used to index into the first level page table. Now, to figure out how many bits we use to index into our second level page table, it's just a matter of subtraction. Because when we're looking at our virtual address, we know that we can split it up into 3 different parts. This part is the page offset. And then these are the bits that we use to index into the first level and the second level. We know that the total size of a virtual address is 48 bits. We know that our page offset takes up 13 bits, and we know that our first level takes up 10 bits. So it's just a matter of subtraction. 48 minus 23 gives us 25, and so we need 25 bits to index into our second level page table. Meaning, of course, that all of our second level page tables will be a lot larger than our first level page table. Now we want to figure out how much memory this virtual page system, or the page table system, takes up in the absolute worst case. So the absolute worst case is that every single second level page table is allocated. Remember, we only need to allocate second level page tables as we need them. So in general, our 2-level page table will take up less memory than a single level page table. But in the worst case, if every single second level page table is allocated, we're going to need a whole lot more memory. So we're going to need the size of the first level page table, where the first level page table we will always have, and that is 1 page, or 8 kilobytes. And of course, 8 kilobytes is 2 to the 13th bytes. And then worst case, we will have 1 second level page table for every single first level page table entry. And we already calculated that we have 2 to the 10th first level page table entries. So we'll do 2 to the 10 times however much space a second level page table would take up. A second level page table has 2 to the 25th entries in it. And we know that each entry takes up 8 bytes. So what we're calculating here is the size of the first level page table plus 1 second level page table for every single first level page table entry. This all comes out to 2 to the 13th bytes plus 2 to the 10th times 2 to the 25th times 2 to the 3rd is 2 to the 38th bytes. And that's how much memory this would take up in the absolute worst case scenario. And now at the bottom here, we consider a case where we only have a single level page table. So in that case, if we change the problem so we only had a first level page table, then if we look at our virtual address again, we no longer have 2 spots that we would use. We no longer have 2 designated spots for the first level page table and the second level page table. We just have the first level offset. And then we have the page offset. And we know still that the page offset is fixed at 13 bits. And so if our address was still 48 bits wide, our first level offset would now need to be 35 bits. Meaning that we would need 2 to the 35th entries in our first level page table. And if each entry is 8 bytes, that means that the total size of the page table in this scenario would be 2 to the 38th bytes, which is slightly better than the absolute worst case second or 2-level page table situation. So that was a brief overview of how you might tackle one of these problems with a bunch of information relating to virtual memory. And hopefully now you'll be better equipped to do these sorts of problems on homework and exams.